I'm going to present the work titled Simplifying Graph-Based Collaborative Filtering for Recommendation for my student, I think, Li He. So I'm Guangdong Xi from University of Technology, Sydney, School of the Computer Science. This is also a joint work with eBay Research US. So I think first, let me a quick review of the background or the context. The recommendation become, I think, prevalent in many applications ranging from the e-commerce, entertainment, and the app recommendation for predicting the user's preference across a lot of product, right? And among, I think, the recommender systems, collaborative filtering is a representative algorithm which can learn the user and also the item embedding from the user-item interaction. And because I think the user and item interaction can be naturally represented as a graph, so recent study started to leverage the graph, a lot of graph-based algorithm. So for example, the graph convolution network for the node embedding. And because I think the GCN-based approach can exploit the high-order user and item information, interaction information, so it can achieve the great success for the recommendation system. So here is some history of the GCN-based recommendation algorithm. So we can see, so the first model was proposed in 2017, which is named, I think, Graph Sage. And also, I think in 2019, the first attempt approach by combining the GCN with a CF approach, which is named, I think, the NG-CF. And recently, I think, more and more, I think, research on how we can combine the GCN, the graph-based approach, with the CF, and also try to simplify the model itself to improve the computational efficiency. So I think among all these approach we can observe, they all, I think, possess the features of the messaging passing, and also they can leverage the high-order collaborative, I think, signal. However, so all of them also, I think, face some challenge, so especially for the large-scale graph structure. So low speed, I think, training, and also stacking many, I think, layers. They may result in the overfitting and over-smoothing. So basically, our work is try to, I think, improve some of the state art in this regard. So how we can simplify the GCN-based approach combining with the CF to make it a more, I think, efficient. And before, I think, our proposal, so let's, I think, just quickly review, so why I think GCN-based method behave, I think, as such, suffering, I think, such, I think, a problem. Okay, so we do, I think, some of the, I think, study to review, I think, the mechanism inside the GCN-based CF approach. So we can observe, I think, the first point is about the message, I think, passing. So we all know that the GCN approach is mainly, I think, pull together the neighborhood information in aggregation for the node, I think, embedding. And also they need to go through some very complicated dot product calculation to achieve that. So in this regard, the limitation of the message passing are the factors are asymmetric. They, I think, fail to capture a varying importance of a different relation, and also they fail, I think, capture the deeper collaborative signals due to the over-smoothing problem. That's first. And the second, I think, in terms of the model inside the node embedding, so most of them, they adopt the feature transformation and also non-linear activation function. So look at, I think, the approach itself. So basically, we are going to see that, right? So this kind of node embeddings, they go through such a mechanism. So here, so our argument is that, so above, I think, two operation can do, I think, a bad job in the node and the graph classification. But however, it cannot, I think, work very well, very useful for the collaborative filtering, because the nature of the user-item interaction, all the node does not, I think, contain a lot of semantic information. For example, in the user-item interaction, so sometimes they only have, I think, an ID of the user or item. So that's our the first argument. The second argument is that, so we believe, I think the initialization of the network embedding so also will play a significant role for the node, I think, embedding calculation. So here, I think the two issues we need to resolve that are, the first one is a large number of the unbalanced, I think, raw data came from the different, I think, network structure. The second is a large scale, so edge cut. So how we can make simplified, I think, the version for the GCN-based model. So here it comes out our proposed, I think, the framework. So basically, we propose a simplified graph collaborative filtering algorithm, which largely simplifies the model design by including only the most essential component in the GCN for more efficient, I think, recommendation. Meanwhile, we also proposed effective partition techniques for reducing the scale of the input graph structure to avoid the infinite, I think, layers of the explicit message passing for the efficient, I think, the recommendation. So particularly SGCF, our proposed model successfully, I think, removes the linear transformation and also the non-linearity operation, and also skip the multi-layers messaging passing structure, and also, I think, use graph as a partition to condense the input and graph the data. So in short, so our major, I think, the attempt for this kind of simplification GCN model is mainly, I think, through these two steps. Okay, so in more, I think, the particular details, our methodology, I think, just as I said, basically undergo, I think, two steps. One is first, I think, the simplified graph convolution module. So basically, I think our model actually will take the weighted sum aggregator to replace the existing feature transformation and also nonlinear activation function. And so I think the model can, in that regard, can simplify the existing model. The hypothesis of our approach is that, again, as I said, so for the kind, I think, the mechanism, so it can works very well for the node and the graph classification, but however, for the CF approach, so we argue that with such a simplified the structure, it can effectively improve the computational cost. And to provide as a theoretical proof, we also conduct the SGC analysis from a convolution, I think, the perspective, and manifest this method as a low-pass type, I think, a filter for the spectrum domain. So in fact, such approach can work as a low-pass type of filter, which can capture the low-frequency signals, so which correspond with smoothing features across a graph in the setting. So basically, I think through such kind of the low-pass type filter, so we argue the approach can partially address the over-smoothing problem often encountered in the GCN-based approach. The second step is about the initialization for the networking embedding. So here, I think we mainly take two steps. The first step to partition the original, I think, the input graph into a number of the subgraph, and which each subgraph, which is in the similar thing range of size. And the second step is about the minimizing the size of the edge card. So the hypothesis here is that, so after the graph partitioned, so once, I think, we have, I think, one node with the updating. So in such case, so all the connecting point connect to this, I think, that point should also need to be updated. So in order to reduce such updating computational cost, so here we adopt, I think, the minimizing the size of the edge card to ensure, I think, the incurred cost will be, I think, minimized. And the last part is about our experiment. So to validate our proposed approach in terms of recommendation performance and also in terms of the improve the efficiency of the cost. So we conduct a comparison. So in a 4 data set. So here I think table 1 lists all the statistic of the 4 data set, and also we make the comparison with 3 kind of the baseline. So this I think include the MF-based method. And second is the networking embedding method, and the last one is the GCN-based approach. And all the baseline are from I think the published work in the KDD, CIR, ICML, and the CIKM. And our comparison and through the experiment can validate our proposed approach can outperform the baseline approach. Baseline, I think, a SOTA approach. So, for example, so we can achieve the 10% improvement on the Amazon, I think, the datebook. And we also conduct the experiment for the validation of improved efficiency. So here I listed some of the experiment. So the table 3 is mainly about the efficiency comparison with the full, I think, training data set. So we compared our SGCF approach with 3 representative algorithms from 3 types of the baseline, and using the epoch count and the time for per epoch and also total times. So from here we're going to see, so our model can always achieve the best performance with the comparison with others. Okay. Table 4, so it's mainly about the efficiency comparison with the same epoch. So for each epoch, so we aim to see so how it different from others. Again, so from the algorithm from result, we can see so in our approach can also achieve a very good result. And the table 5 is about the population study. So we aim to examine so how with a different setting of the K, so how our approach performance are different from others. Use I think 2 data sets. One is the Amazon, another one is a Koala. And the last comparison data set is about the effect on the over-smoothing, I think, the effect. So here, I think we run our experiment to use, I think, 2, I think, the data set, and also, I think, make comparison for the user item embedding. So from here, I think that we compare our approach with graph partition and also non-graph partition. So we are going to see, so one is represented as a red, another one is blue. So we are going to see, so with the graph partition approach, so the user and item embedding, so they expect, I think, the large difference compared to the without, I think, partition. So this result can partially, I think, validate our conclusion that, so with our proposed approach, it can somehow overcome the smoothing problem. Okay, so finally, I think let's quickly, I think, conclude. So in this work, we empirically studied the simplification of the GCN-based CF approach by removing the nonlinear transformation in the GCN model and replace it with only the linear embedding propagation setting. To reduce the over-smoothing effect introduced by the higher layers of graph convolution, we designed a condensed graph learning process for the input network, and the extensive experiment result conducted on 4 datasets can clearly show the effectiveness and the efficiency of our proposed approach. And for the fair comparison, we also, I think, released the our code in open source platform for, I think, more comparison and also for the evaluation. Okay, thank you for attention. Let's come to end of my presentation.